In this video, we're going to explore the use of concentrations in chemical analysis. Earlier, we've looked at how we can use stoichiometry and molar masses in order to relate the masses of two things involved in a chemical reaction. However, if we don't have a solid, and instead we are working with solutions, we need a way to use those in order to do the same thing. And so this leads us to looking at the concentration, or the amount of something that is dissolved in solution. When discussing concentrations, we can do so in a couple of ways. We can either discuss them qualitatively, as either concentrated or dilute solutions, as just a qualitative measure of how much substance is dissolved, or we can look at them from a quantitative perspective and mathematically specify the actual amounts of solute and solvent in the solution. We will first begin with a discussion of molarity, which is a very key component in looking at some stoichiometry of solutions. In order to discuss concentration of solutions, we need to define a couple of terms. A solution is composed of a solute and a solvent. The solute is the substance which is dissolved and is present in a lesser amount. The solvent is the substance which is doing the dissolving and is present in the greater amount. Typically, in chemistry, we will be using water as our solvent. One of the primary methods of measuring concentration in chemistry is by the use of molarity. Molarity is equal to the moles of our solute per liter of our solution. And it's a very easy calculation. All we have to do is take our moles of solute and divide that by our liters of the solution. And so in this case, if we're looking at the concentration of a sodium chloride solution, which we represent in brackets around our compound just mean the concentration of that solution. And so if the concentration of this sodium chloride solution is 1 mole in a liter of solution, then we take our 1 mole divided by our 1 liter, and we get what we refer to as a 1 molar solution. Capital M stands for molar. Molarity is just another conversion factor like many others that we've looked at. It's our number of moles divided by our number of liters. And so, for instance, if we have a 0.025 molar solution of ammonium nitrate, then that equals 0.025 moles of ammonium nitrate per liters of ammonium nitrate. Or, depending on what I'm doing for a calculation, I can also think of that as 1 liter of my solution contains 0.025 moles of ammonium nitrate. So just like any conversion factor that we've used, you can use this in whichever way you need, depending on your calculation. Let's take a look at a fairly typical molarity problem. In this problem, we have 0.395 grams of potassium permanganate dissolved in enough water to give us a 250 milliliter solution. And we want to know the molarity of that potassium permanganate. Let's take a look back at a graphic we've seen a few times already. We've looked at this graphic before in comparing atoms and moles and grams and seeing how to convert back and forth. Now we're going to be able to add in molarity. And so we can see that if we're starting with our grams, as we've done before, we need to first divide by our molar mass to get to our number of moles, and then we can simply divide by our liters in order to find our molarity. And so let's do that for this problem. And so let's take a look at how that calculation plays out. We began with 0.395 grams of potassium permanganate, and our first step is to convert to moles, so we're going to divide by our molar mass to get 0.0025 moles of potassium permanganate. We're then going to divide that by our liters of solution. Now take note here that the volume does have to be in liters for our molarity calculation. And so we have to convert our 250 milliliters to 0.250 liters. And so 0.0025 divided by 0.25 gives us a final concentration of 0.0100 molar. Take note of the significant figures in this calculation as well. Let's look at another example, following the same pathway. If we dissolve 5 grams of nickel chloride hexahydrate in enough water to make 250 milliliters of solution, we go about this in the same way. We're first going to calculate our moles of our solute by dividing by our molar mass. We then take that number of moles, divide it by our liters of solution, in order to obtain a molarity of 0.0841 molar. Sometimes we want to know what the molarity is of specific ions in our solution. And so we have to remember that in an aqueous solution, our ionic substances will break apart into their constituent ions. And so in this case, a solution of copper 2 chloride will actually consist of copper 2 ions and chloride ions in a 1:2 ratio. And so this means that if we have a 0.3 molar solution of copper 2 chloride, our concentration of copper ions is going to be 0.30 molar, but our solution of chloride ions will be double that, because for every 1 unit of copper 2 chloride, I produce 2 ions of chloride. And so our chloride concentration in this solution will be 0.60 molar. One of the more common procedures in a chemistry lab is preparing a solution that has a known concentration. In order to do this, we will often use a volumetric flask. The whole purpose of a volumetric flask is simply to make solutions of a known concentration. In this case, this 250 milliliter volumetric flask will be used to make 250 milliliters of solution. And so what we'll do first, in this case making a potassium permanganate solution, is we'll dissolve the amount of potassium permanganate we need in a little bit of water in order to get it to dissolve. We will then add water until we get up to the mark, which signifies 250 milliliters. It's important for us to remember that the volume of a solution is equal to the total volume of the entire solution, the solute and the solvent together. Therefore, in a case like this, we do not simply add 250 milliliters of water, but we add enough water so that our final total volume is 250 milliliters. And so let's take a look at how we do this in practice. If we want to, for instance, make 500 milliliters of a 0.250 molar lithium carbonate solution, we need to know the mass of lithium carbonate to use in order to make this. And so we can set up a dimensional analysis setup. We want to make 500 milliliters. We know that we're going to need liters for molarity, and so we need to convert this to liters first. Now we can use our molarity in order to convert over to moles of lithium carbonate that we'll need. Remember that the units of molarity are moles per liter, so we have our moles of lithium carbonate per liters of solution. If we stopped right here, this would tell us how many moles of lithium carbonate we need. But our lab balances don't measure in moles, they measure in grams. And so now we can use our molar mass to convert over to grams. And if we look at how our units worked out, our milliliters cancel out, liters cancels out, moles of lithium carbonate cancels out, and I'll be left with grams of lithium carbonate for a final result of 9.24 grams of Li2CO3. And so this means that I'm going to measure out 9.24 grams of lithium carbonate, dissolve that in just enough water so that it dissolves in a 500 milliliter volumetric flask, and then add enough water up to the mark of 500 milliliters. Let's take a look at what our concentration of lithium ions would be in this solution. Let's recall what happens when I dissolve a solid lithium chloride sample in water. It will actually break apart into lithium and carbonate ions in a 2-to-1 ratio. Therefore, for every 1 unit of lithium carbonate, I will actually form 2 lithium ions. Therefore, if I have a 0.25 molar lithium carbonate solution, I have 2 moles of lithium per every 1 mole of lithium carbonate, and so I have 0.500 molar lithium plus. Let's say I'm running a reaction in which I need 0.0100 moles of lithium carbonate. I'll need to know what volume of my solution that I want to deliver that many moles. So we can use our units of molarity in order to see how to set this up. We want 0.0100 moles of lithium carbonate. We know that our units of molarity are moles per liter, and I want moles to cancel out. And so that's going to go down bottom in my dimensional analysis setup with liters on top. Remember, molarity is just another conversion factor. We can set it up however we want to. And so this tells us that I will need 0.04 liters of solution, or 40 milliliters of 0.250 lithium carbonate will contain 0.0100 moles of lithium carbonate. Maybe I have a certain mass of lithium carbonate that I need to deliver with this solution. And so we'll need to calculate what volume of 0.25 molar lithium carbonate will contain that mass. In this case, we're looking for 8.00 grams of lithium carbonate. We're going to use a very similar setup as we did in the last example, only here we're starting with grams, and so first we have to convert to moles of lithium carbonate using our molar mass. And then finally, we can use our molarity just as we did in the last example. We have a 0.250 molar solution. And so we calculate that out, and we find that we're going to need 0.433 liters of this solution, or 433 milliliters of 0.25 molar lithium carbonate will contain 8.00 grams of lithium carbonate. Sometimes when we're preparing a solution, we are doing so from another, more concentrated solution to start with. And so in this example, we are starting with a 0.100 molar potassium chromate solution, but we want to have a 0.001 molar solution. And so we need to know how much of that initial solution we need to use in order to then dilute up to the amount that we're looking for. When doing these sorts of dilution preparations, in order to do these dilution calculations, we use what we call the dilution equation, or sometimes called the M1V1 equation. Note that you might sometimes see this as a C1V1 or a C2V2, because these calculations will actually work just as well with any units of concentration. We're going to focus on molarity, but you could use any other different concentration units in the exact same way. Note in this equation that our moles that we have in our initial sample will be equal to the moles that we have in our final diluted sample. The amount of moles is not going to change. The concentrations and the volume will, but our amount will stay the same. And so when we're looking at this equation, the M1 is the molarity of our initial solution, so our more concentrated solution that we are starting from. V1 will be the volume of that initial solution, M2 will be the concentration of our diluted solution, so usually the concentration that we're looking for. And V2 will be the volume of that new diluted solution. This example is a very typical example of how we will use the dilution equation. Many stockrooms contain concentrated acids. It is just easier for us to store them in this way. However, for lab use, we will very often use much more dilute solutions. And so we want to know then how much 12 molar hydrochloric acid we would need in order to prepare 100 milliliters of a 1.0 molar solution. And so we set up our dilution equation. Our M1V1 equals M2V2. Our M1 in this case is our 12 molar solution that we are starting with. That is our stock solution. And so we have 12 molar times an unknown volume. This is what we're looking for. We want to know how much of this 12 molar we're going to need. And that's going to equal our M2, which is the molarity that we are trying to obtain, times the volume that we are trying to obtain. It's also important to note here that in this case, volume does not have to be in liters. You can use whatever volume measurements that are convenient for you. You just have to make sure that they're consistent. In other words, we're starting with milliliters here. That means when I solve for x, x will also be in milliliters. And so we now solve for x. X will equal 1 times 100 divided by 12, which works out to 8.3 milliliters. And so this tells me that I want to take 8.3 milliliters of the 12 molar solution and dilute that 8.3 milliliters up to 100 milliliters. In doing so, I will then have 100 milliliters of 1.0 molar hydrochloric acid. Let's look at another example. In this example, we're starting with 0.025 molar ammonium nitrate, and we want to use enough of that in order to make 25 milliliters of a 0.020 molar solution. And so we will once again use our dilution equation, M1V1 equals M2V2. Our M1 is our stock solution of ammonium nitrate, 0.025. We want to know how much of that to use. That's our X. We are looking for a 0.020 molar solution, and we want 25 milliliters of that. And so there's our setup. We solve for X, and we find that we need 20 milliliters. And so in other words, if I take 20 milliliters of my 0.025 molar solution, and I dilute that 20 milliliters to 25 milliliters, I will then have a 0.020 molar solution. In this case, we want to know what a new concentration is. If we take a certain amount of our stock solution of nitric acid and dilute that. And so again, it's simply M1V1 equals M2V2. And so now we know that our M1 is our initial concentration of nitric acid. That's our 14.8 molar. And now we're taking a certain amount of that. We're taking 25 milliliters of that solution. We don't know what the new concentration is. That's what we're looking for. But our final volume is 1.5 liters. Again, it doesn't matter what units we use for volume, but we need to stay consistent. And so I'm going to convert 1.5 liters to 1,500 milliliters. I solve for X, and I find a new molarity of 0.25 molar nitric acid. Molarity is one of the more widely used concentration units in chemistry. Depending on what we're doing, though, we might need to use other concentration units. And other scientific disciplines sometimes use other units as well. Later on in chemistry, you may have to work with units of molality, for instance, in which we're no longer looking at our volume of our solution, but we have our moles of solute divided by our kilograms of solvent. Sometimes we express concentrations as a percentage, and so we might look at a weight to weight, a volume to volume, or a weight to volume. In other words, if we have a 5% weight to weight solution, then that means that 5% of our solution is going to be our solute. And so we would express that maybe as 5 grams of our solute per 100 grams of our solution. And it would be similar for the other percent concentrations. Sometimes it's convenient for us to express concentration in terms of parts per million. This seems to be especially common if we're looking at concentration of things like trace metals. A 1 ppm solution means that I would have 1 gram of my solute per 1 million grams of the total solution. Let's look at how we might convert back and forth between some of the concentration units. And so in this example, if I have a 78 ppm calcium ion concentration, I might want to convert that to molarity. And so let's remember that 1 ppm means that I have 1 gram of my solute per 1 million grams of my solution. And so, let's scale this by a little bit. Let's divide both sides here by 1,000. And so I would have 0.001 grams of my solute per 1,000 grams of solution. Or I would have 1 milligram of solute per 1,000 grams of solution. Now, aqueous solutions are usually so dilute, the concentration is usually so low, that we can assume the density is equal to the density of water at 1 gram per milliliter. And so in that case, that 100 grams of solution is really equal to 1,000 milliliters, or 1 liter. And so what this really means for us is that a 1 ppm solution is equal to 1 gram of our solute per 1 liter of our solution. This then makes it very easy for us to convert from ppm over to molarity, considering that molarity is in terms of liters of solution. And so, if I have a 78 ppm calcium ion solution, that really means that I have 78 milligrams of calcium per liter of solution. And so I can convert that 78 milligrams over to grams. I can then use the molar mass of calcium to convert to moles. And if I look at how my units work out there, milligrams cancels out, grams cancels out, and I'm left with moles divided by liters, which are our units of molarity. And so in this case, I would have a 0.0019 molar solution of calcium ions. Sometimes we're given a percentage concentration, and we might want to convert that over to molarity. In this case, we're told that we have a 5% hydrogen peroxide solution, and we want to know what the molarity of that is. You'll find that you won't always be told if it's a weight, volume, etc. percentage. If you look, for instance, on a bottle of peroxide, it simply tells you that it's 3%. It doesn't necessarily say if that's weight or volume. In many of these cases, though, we can assume a density, again, of 1 gram per milliliter because it is so dilute. And so since it is simply 1 gram per milliliter density, it doesn't really matter if it's weight to volume or volume to volume because those numbers would work out to be the same. And so in this case, we're going to go ahead and assume that this is a weight to volume ratio. And so what this means is that there are 5.00 grams of H2O2 per every 100 milliliters of our solution. And so we can then use that in order to convert to molarity. If we simply multiply the top and bottom by 10 here, that tells us that we've got 50.0 grams of peroxide per 1,000 milliliters of solution, or 50 grams per 1 liter. And so if we have 50 grams of peroxide per liter of peroxide, it's starting to look a lot like molarity, only we have to convert over to moles. And so we use our molar mass of peroxide. And again, if we look at our units, we'll see that grams will cancel out. We're going to be left with moles of H2O2 over liters, which are the units of molarity. And so this works out to be 1.47 molar. And so a 5% hydrogen peroxide solution is equal to 1.47 molar. So in this video, we've explored many of the different aspects of solution concentration. This will come in very handy for us as we begin to look at reactions that start from a solution rather than starting from a solid. I hope this has been helpful. If you're looking for more assistance, be sure to visit the website.